The future doesn't always arrive with an announcement. Sometimes, it hides behind guarded gates, mirrored glass walls, and silent corridors humming with power. Somewhere in southern Africa, beyond the noise of mainstream tech capitals, stands one of the most mysterious innovation hubs in the world, the headquarters of Maxwell Chikumbutso. This is not just a building. It is a statement. And today we're stepping inside. 4. From the outside, the structure feels like it was designed by tomorrow itself. Polished steel curves into tinted glass. Solar arrays stretch across the rooftop like mechanical wings. Security cameras rotate silently, tracking every movement with precision. There are no flashy logos screaming for attention, only quiet confidence. As the doors slide open, the first thing you notice isn't the machines. It's the silence. Not the absence of sound, but controlled sound. The soft hum of processors. The whisper of air filtration systems. The distant rhythm of automated assembly arms moving in perfect synchronization. This is where ideas stop being theories and start becoming hardware. We move through a corridor lined with transparent OLED displays. On them, animated schematics of electric drivetrains rotate in midair. Prototype propulsion systems are broken down layer by layer in holographic projections. Engineers walk past without spectacle. No loud conversations. No chaos. Just focus. In the central atrium, a full-scale concept vehicle sits under precision lighting. No branding. No marketing banners. Just raw engineering presence. The body lines are sharp, aerodynamic, sculpted for efficiency rather than applause. 4. Above the vehicle, suspended robotic arms adjust panels with microscopic accuracy. Every movement is calculated. Every measurement verified by AI-driven systems monitoring tolerances down to fractions of a millimeter. This isn't a showroom. It's a proving ground. Further inside, we enter the propulsion research wing. Here, experimental energy systems are tested in reinforced chambers. Thick composite walls isolate vibration. Digital dashboards display torque output, energy conversion rates, thermal mapping. Some systems are conventional evolutions of electric architecture. Others are not. Whiteboards filled with equations suggest ambitions beyond current mainstream engineering. Energy independence. Self-sustaining platforms. Systems designed to minimize reliance on external infrastructure. Whether every claim can withstand global scrutiny is a debate for analysts. But ambition? Ambition lives here, without apology. We continue deeper into the facility. A secure biometric checkpoint slides open to reveal the electronics lab. Circuit boards are etched by precision machines under sterile conditions. Microcontrollers are assembled using automated pick-and-place systems operating at speeds almost too fast to follow. Technicians inspect boards under magnification lenses, ensuring no imperfection escapes detection. 4. Large digital walls display live diagnostics from prototype vehicles undergoing stress tests in remote environments. Desert simulations. Mountain inclines. Urban stop-and-go cycles. Everything is data. Everything is measured. And in a glass-enclosed strategy room overlooking the entire production floor, conceptual sketches of aircraft designs line the digital boards, a reminder that this headquarters does not confine itself to roads alone. The atmosphere shifts as we approach the energy division. Massive battery modules are arranged like architectural sculptures. Cooling systems pulse rhythmically. Engineers analyze degradation curves, optimizing for longevity rather than short-term performance bursts. Here, the mission feels bigger than transportation. It feels geopolitical. Energy autonomy has always shaped global power structures. And inside these walls, the intention is clear: reduce dependence. Build internal capability. Control the source. We pass through a prototype storage vault. Experimental chassis platforms rest on adaptive stands. Some designs are radical, narrow profiles, enclosed wheel systems, lightweight composite frames engineered for maximum strength-to-weight ratios. Others look ready for immediate production. But none are accidental. Every bolt, every weld, every circuit pathway. Intentional. In the software integration wing, programmers sit before curved ultra-wide displays, refining control algorithms. Autonomous assistance features are simulated in real-time digital twins. Failsafes are layered within failsafes. The future here isn't just mechanical. It's computational. A server room pulses behind reinforced glass, rows of synchronized processors managing design simulations and encrypted research archives. The cooling systems exhale softly, maintaining perfect thermal equilibrium. This headquarters does not feel experimental. It feels prepared. And yet, the most intriguing part isn't what's visible. It's what remains classified. Certain doors remain sealed. Certain labs require clearance beyond standard credentials. Certain prototypes are covered, not for aesthetics, but for strategic timing. Innovation, after all, is as much about revelation as it is about development. As night falls, the exterior lighting activates. The building glows against the skyline, not aggressively, but deliberately. Solar reserves transitions seamlessly to internal storage systems. The facility remains operational, uninterrupted. Inside, teams rotate shifts. Progress does not sleep. And somewhere within these walls, new blueprints are being drafted. New propulsion theories are being refined. New vehicles are being assembled in silence. This headquarters is not just about technology. It is about narrative, about proving that advanced engineering can rise from places the world never expected. That innovation is not geographically exclusive. That the future does not require permission. But the deeper question lingers as we walk back toward the entrance. What happens when ambition meets scalability? Can these systems transition from prototype to global production? Can the headquarters evolve into an industrial ecosystem? The doors slide closed behind us. The lights dim slightly. But inside, the machines continue moving. And in that unseen lab, beyond layered security protocols and encrypted access panels, a small team stands around a prototype unlike anything displayed on the main floor. No press cameras. No promotional banners. Just quiet intensity. A transparent casing reveals a compact energy core mounted at the center of a lightweight chassis platform. Fiber optic cables pulse faintly, transmitting data into overhead monitoring systems. The engineers aren't celebrating. They're watching, monitoring fluctuations measured in microseconds, tracking efficiency percentages that shift in decimals, listening, not with ears, but with instruments calibrated to detect imperfections invisible to human senses. 4. One screen flashes a performance spike. Not dramatic, not explosive, but meaningful. A subtle increase in output stability under simulated load conditions. A breakthrough? Maybe. Or maybe just one more step in a 1,000-step process. Because inside this headquarters, progress isn't measured in viral moments. It's measured in iteration. We move upward to the Materials Science Division, a quieter, colder wing of the facility. Here, raw materials are stress-tested under extreme conditions. Hydraulic rigs bend alloy samples to their breaking points. Laser scanners analyze microfractures invisible to the naked eye. Lightweight composites are subjected to impact simulations replicating high-speed collisions. Data scrolls continuously, forming patterns only trained engineers can interpret. If propulsion is the heart of innovation, materials are its skeleton. And without strength, ambition collapses. Down the hall, a wind tunnel chamber dominates an entire section of the building. A scale model vehicle sits mounted on precision supports as high-velocity air surges around it. Colored smoke trails reveal aerodynamic inefficiencies. Adjustments are made in real time. Drag coefficients shrink by fractions. Fractions matter. Because when you scale production, fractions become fortunes. 4. Beyond physical engineering, the Data Analytics Command Center feels almost like a space agency control room. Massive LED walls display live metrics from prototype fleets operating in undisclosed testing zones. Battery discharge cycles. Thermal stress readings. Autonomous decision logs. Everything feeds back here. Artificial intelligence models refine predictive maintenance schedules. Algorithms anticipate component fatigue before failure occurs. Software updates are drafted even before issues fully manifest. Prevention over reaction. Strategy over spectacle. In a smaller, more private conference chamber, digital world maps illuminate potential expansion zones. Supply chain routes are traced with precision. Manufacturing scalability models rotate in three-dimensional projections. This is where vision collides with reality. Because building a prototype is one challenge. Building an ecosystem is another. The conversation shifts from voltage outputs to logistics networks. From torque curves to international compliance standards. From engineering purity to economic feasibility. Ambition must survive contact with the real world. And yet, throughout every department, one theme remains consistent. Self-reliance. Energy systems designed to reduce infrastructure dependence. Manufacturing tools engineered to operate efficiently within local resource constraints. Software frameworks developed in-house rather than outsourced. It's not just about competing globally. It's about redefining origin stories. 4. We descend toward the lower levels, areas rarely discussed publicly. Here, acoustic insulation thickens. Lighting becomes more focused. Experimental propulsion rigs are mounted within reinforced bays, isolated from the rest of the building. When activated, the chamber vibrates with restrained power. No theatrical explosions. No dramatic sparks. Just controlled force, disciplined, contained. Technicians observe from behind ballistic glass panels as data streams across their tablets. Cooling systems engage automatically. Stabilizers compensate for micro-oscillations. Every test leaves a digital footprint. Every anomaly is archived. And somewhere above ground, in the polished executive suite overlooking the campus, long-term strategy documents evolve continuously. 5-year projections. 10-year manufacturing targets. Cross-industry collaborations. Because a headquarters like this is not built for a single invention. It is built for continuity. As dawn approaches, faint sunlight filters through the upper glass panels. Night shift engineers exchange brief nods with incoming teams. Coffee cups replace energy drinks. Monitors remain active. Simulations continue uninterrupted. There is no dramatic off switch here. Innovation operates on rotation. And as we stand once more in the central atrium, that concept vehicle under the precision lights looks different now. Not just as a machine, but as a symbol, a prototype of something larger. An assertion that advanced technology does not belong exclusively to Silicon Valley, Shenzhen, or Munich. It can emerge wherever determination meets discipline. But questions still ripple beneath the polished floors. Can secrecy coexist with global trust? Can bold claims withstand industrial-scale scrutiny? Can localized innovation transition into global infrastructure? Inside these walls, confidence suggests yes. Outside, the world waits for proof. And somewhere, behind another secured door we still haven't opened, a new blueprint is loading onto a digital screen, pushing limits that most would consider impossible. The digital blueprint stabilizes on the central display, a modular platform unlike the previous prototypes. Instead of designing a single vehicle, the architecture is adaptable. The same core frame could support a compact urban car, a long-range transport vehicle, even a light tactical platform. Flexibility, scalability, survival. Engineers begin running structural simulations. The model fractures on screen, not physically but mathematically, stress points lighting up in red. Reinforcement zones are adjusted. Composite layering is recalculated. The red fades to amber, then to green. A quiet exhale moves through the room. Not celebration. Validation. 4. Across the corridor, another team integrates propulsion mapping into the same modular framework. Software architects synchronize energy distribution algorithms with physical drivetrain tolerances. Every component must communicate seamlessly. Because in this headquarters, hardware without software is incomplete. And software without hardware is theoretical. The integration lab becomes a symphony of silent coordination. Diagnostic tools connect wirelessly. Firmware builds compile in real time. Simulation environments replicate unpredictable real-world scenarios, abrupt terrain shifts, extreme climate swings, unstable grid conditions. Failure is not feared here. It is invited. Each breakdown in simulation is dissected, understood, refined. Somewhere else in the building, a prototype undergoes environmental testing. Artificial climate chambers cycle between scorching heat and freezing cold within hours. Sensors monitor expansion rates, battery response curves, insulation integrity. Durability is not a feature. It is a requirement. 4. Back in the analytics center, predictive modeling systems begin projecting manufacturing capacity scenarios. What happens if demand doubles? What if supply chains contract? What if regulations shift unexpectedly? Contingency plans stack upon contingency plans. The headquarters feels less like a factory and more like a chessboard. Every move calculated, every risk mapped, every advantage quietly positioned. As afternoon light pours through the upper atrium, a private demonstration begins for a small group of internal stakeholders. No media presence. No dramatic unveiling music. Just a live systems activation. The prototype powers on. No roar. No vibration. Just a subtle illumination across the dashboard interface. Energy flow stabilizes within safe thresholds. Drive modules engage with near imperceptible motion. On the monitoring screens above, performance metrics scroll upward, efficiency ratios climbing, thermal outputs staying controlled, stability curves flattening into near perfection. One engineer whispers a number. Another nods. It's better than expected. But even in this moment, adjustments are suggested. Micro-optimizations, software tuning, material substitution possibilities. Perfection here is never final. It's iterative. We step outside briefly to observe the test track concealed behind the main complex. High fencing surrounds a winding asphalt course embedded with sensors beneath the surface. Cameras mounted along the perimeter track every centimeter of movement. The prototype glides forward. Acceleration is smooth, controlled, deliberate. Braking systems respond instantly. Autonomous guidance assists in tight curves, calculating friction coefficients in milliseconds. There is no dramatic skid. No cinematic drift. Just precision. 4. Inside the control room overlooking the track, analysts dissect the data in real time. Every turn generates terabytes of insight. Every straightaway refines acceleration mapping. This isn't about proving a concept anymore. It's about preparing for reality. As dusk approaches once again, the headquarters shifts into its evening rhythm. Production prototypes return to secured bays. Engineers archive daily findings into encrypted servers. Strategy teams recalibrate projections based on fresh data. And somewhere above the main atrium, in a minimalist office lined with conceptual sketches and early prototypes, a long-term vision continues evolving. Not just vehicles. Not just energy systems. An ecosystem. A vertically integrated technological foundation capable of sustaining itself, from design to deployment. But ambition at this scale always carries weight. Questions linger in the background of every achievement. How will global markets respond? Will regulatory bodies embrace or challenge unconventional systems? Can innovation born outside traditional power centers scale without compromise? Inside these walls, the response is silent but steady. Build first. Refine relentlessly. Reveal strategically. The headquarters lights brighten as night settles in once more. Solar reserves transition smoothly. Internal storage systems balance load distribution without interruption. Machines resume their rhythmic motion. Design software continues rendering possibilities. Engineers rotate shifts again. And in that restricted lab we glimpsed earlier, the modular platform is already evolving. Version 2.0 loading onto the central display. Structural weight reduced further. Energy efficiency recalculated upward. A new variable introduced, something experimental, something not yet seen outside these reinforced walls. The team leans closer. Parameters are adjusted. Simulations initiate. And as digital wind sweeps across a virtual landscape on the main screen, the model moves forward, Faster, lighter, more stable than before. No announcement is made. No headlines flash across global media. But within this futuristic headquarters, the next chapter is quietly unfolding. The experimental variable begins to take shape on the display, not just as a component, but as a system layered into the architecture itself. It isn't a dramatic redesign. It's subtle, a redistribution of energy flow pathways, a refinement in conversion efficiency, a smarter synchronization between storage and propulsion. Incremental, but powerful. Engineers initiate a full-spectrum systems simulation. The digital twin of the vehicle now operates inside a hyper-detailed virtual environment, complete with fluctuating terrain resistance, unpredictable weather models, even simulated infrastructure failures. The idea isn't to prove perfection. It's to challenge resilience. 4. On a massive curve display, performance data surges in waves. Efficiency curves hold steady under stress. Thermal signatures remain controlled. Autonomous recalibration systems activate without human intervention when the virtual environment destabilizes. And then, deliberately, the simulation engineers introduce a failure. Grid instability, energy fluctuation, unexpected load demand spike. The system hesitates for a fraction of a second, then compensates. Backup pathways activate. Energy is redistributed. Non-critical systems temporarily scale down to preserve core functionality. Stability returns. The room stays quiet, not because it worked, but because now they know where it almost didn't. The flaw, microscopic but measurable, is logged. Engineers dissect the algorithm responsible. Code is rewritten in sections. Hardware tolerances are adjusted by margins almost invisible to anyone outside this building. Iteration never ends here. Meanwhile, in another wing, the manufacturing automation team is refining robotic calibration sequences. Assembly arms move with choreographed precision, installing modules onto skeletal frames with zero wasted motion. 4. Each robotic joint is monitored by embedded sensors feeding data into a centralized AI oversight system. If alignment drifts by even a hair's width, corrective adjustments are deployed instantly. This is scalability being engineered before mass production even begins. Because prototypes prove possibility, but automation proves sustainability. Back in the strategic planning suite, digital supply chain models begin integrating regional sourcing strategies. Rare materials are analyzed for availability. Local alternatives are evaluated. Dependency reduction becomes a recurring theme in every projection. The headquarters isn't just building machines. It's building independence. Downstairs, a long-term battery endurance test has been running for weeks. No publicity. No dramatic updates. Just continuous cycling, charge, discharge, thermal exposure, rest, repeated thousands of times. A technician checks the degradation curve. It's flatter than anticipated. Longevity improves projections for market viability. Maintenance intervals extend. Cost efficiency strengthens. The data is transmitted upstairs. Adjustments ripple outward. In the autonomous development lab, new sensor arrays are being tested in low-visibility simulations. Artificial fog fills a sealed testing chamber while LiDAR systems pulse invisibly through the haze. Camera feeds blend with radar inputs. Machine learning models attempt to interpret imperfect information, because the real world is imperfect, and technology that only works under ideal conditions is fragile. 4. As midnight approaches again, the headquarters feels alive in a different way. Fewer voices, more screen glow, more machine rhythm. A senior engineer stands alone before the main simulation board, reviewing cumulative progress from the past 72 hours. Efficiency gains, incremental but steady. Structural weight, reduced again. Software stability, improved under stress conditions. But scalability challenges remain. Manufacturing throughput targets need refinement. Regulatory testing frameworks must be navigated carefully. Market trust must be earned, not demanded. He adjusts one final parameter in the modular system architecture, a recalibration that slightly redistributes internal energy buffering across subsystems. Small change. Large impact. A new simulation begins. The digital prototype accelerates across a virtual terrain map. Power draw remains balanced. Thermal load disperses evenly. Autonomous steering corrections are smoother. Projected range increases by another measurable margin. No applause fills the room, just acknowledgement. Because inside this headquarters, breakthroughs don't echo. They accumulate. Outside, the world still debates. Analysts speculate. Skeptics question. Supporters anticipate. Inside, none of that noise penetrates the workflow. There is only development, only refinement, only the next version. And in that secured lab at the core of the complex, a secondary project, one we've only glimpsed in shadows, begins activating its first stage prototype. It's not shaped like a conventional vehicle. Its silhouette is unfamiliar. Energy modules align vertically rather than horizontally. Structural reinforcement patterns suggest applications beyond urban roads. The team powers it on. A low-frequency vibration hums through the chamber, controlled, stabilized, monitored. Data streams surge across overhead displays. Parameters adjust automatically. And as the system stabilizes under its own internal logic, a realization settles quietly among the engineers gathered around it. This headquarters is not chasing the present. It is preparing for a future that hasn't fully revealed itself yet. And the next leap forward is already loading onto another screen. The room grows still as the secondary prototype completes its initialization sequence. Stabilization indicators shift from amber to green. The low-frequency vibration settles into a steady rhythm, not chaotic, not aggressive, but controlled. Contained power. Engineers exchange brief glances. No one rushes to declare victory. Instead, diagnostics begin immediately. Structural feedback loops are analyzed. Energy redistribution curves are mapped. Autonomous calibration routines are stress-tested without warning. The system holds. Outside the chamber, behind reinforced observation glass, analysts watch performance metrics cascade down massive displays. Thermal signatures remain within predicted limits. Structural integrity reports show no unexpected strain. Internal redundancy protocols respond flawlessly when artificial disruptions are introduced. It works, not perfectly, but reliably. And reliability is the currency of real-world innovation. As dawn approaches once again, faint sunlight cuts through the upper glass panels of the headquarters atrium. The building feels different now, not because of one dramatic breakthrough, but because of cumulative progress. Version after version. Iteration after iteration. Refinement after refinement. In the executive strategy suite overlooking the complex, long-term deployment maps update automatically with the latest performance data. Production timelines adjust slightly forward. Risk models narrow. Confidence margins expand, cautiously, strategically. Because ambition without discipline collapses. But ambition refined through relentless testing becomes infrastructure. On the test track outside, the modular prototype performs one final early morning run. Smooth acceleration. Balanced energy output. Autonomous systems reacting in seamless coordination. No spectacle, just precision. Inside the headquarters, teams rotate shifts once more. Night engineers brief morning teams. Data logs are archived. Fresh simulations are queued. The rhythm continues. There is no grand unveiling. No dramatic curtain drop. Just a quiet understanding shared by everyone within those walls. The future is not built in a single announcement. It is built in layers. In silence. In discipline. This headquarters is more than steel and glass. It is a proving ground for ideas once dismissed as improbable. A laboratory for energy independence. A workshop for modular mobility. A command center where engineering meets long-term vision. And whether the world embraces it immediately or challenges it rigorously, one truth remains undeniable. Innovation is happening here. Deliberately. Relentlessly. Strategically. As the main doors slide open and close with their usual precision, the complex continues operating without pause. Machines hum. Code compiles. Simulations render new possibilities. The building stands quietly against the skyline, not demanding attention, not chasing applause. Simply preparing. Because somewhere inside Maxwell Chikumbutso's futuristic technology headquarters, another blueprint is already forming. Another iteration is already refining. Another system is already stabilizing.